Problem number 11. W is a solid region with these bounds, region in three-dimensional space. F is a vector field with this formula right here. What do we want to do? We want to verify the divergence theorem. So that means we will calculate the triple integral over W of the divergence of F, get some answer. We'll calculate out the flux of F itself over the boundary of W, get some answer, and we want to see that those two are the same thing. Okay, so what calculations do we have to do? Let's start off with the left calculation. I guess I wrote this in the reverse of how I usually write this. First off, the divergence of F, the partial derivative of this with respect to X is 1. The partial derivative of this with respect to Y is 1. The partial derivative of this with respect to Z is -3. So we add those up, and so we are integrating -1 here. Before I do anything else, let's just draw a quick picture of what this region is looking like here. So Z is at least 3, but it's under a downward opening paraboloid here at 4. And so this is the region in question here. The easiest way to set up bounds for this triple integral would be in cylindrical coordinates. So theta would be from 0 to 2 pi. R would be from 0 to right here. This would correspond to R is 1. And we can see that by setting these two equal to each other. 1 is 3 equal to 4 minus x squared minus y squared. It's when x squared plus y squared is equal to 1. R is 1 there. And then our Z bounds then. Z is at least 3, at most 4. Of course, this becomes R squared here. So this first triple integral, 0 to 2 pi, 0 to 1 for R, 3 to 4 minus R squared. We are integrating the divergence there, -1. Then we throw in the R, dz, dr, d theta. This is a relatively straightforward integral to evaluate. Let me just write down the final answer here. You would end up with -pi/2. Okay, so this is one side of the divergence theorem. Now we need to do this side, the flux integral F over the boundary. The boundary of W will have two parts. The top part, the paraboloid, the bottom part is a downward facing flat disk there, and the plane Z is equal to 3. Okay, so let's do each of those in turn. Let's start off with the flat disk opening downwards, oriented downwards, I should say here. How do we parameterize this? Well, this is characterized by just having Z equal to 3. So there's a perfectly good parameterization. Of course, x squared plus y squared can be at most 1. For a normal vector here, it's not too hard to calculate out that we end up with 0, 0, -1. So usually, one of those needs to be in x's. Usually I write down r sub x cross r sub y. In that case, we would get 0, 0, +1, but that's oriented in the wrong direction. We want 0, 0, -1. Okay, so we have ry cross rx. Okay, great. And what else do we need here? We need f evaluated at r of xy. So what is f? Let's bring this back here. So y and x just stay put, and then z gets replaced by 3. So with 1 minus 3 times 3. And when we calculate out the dot product of f with the normal vector, so this dot product, this will give us 0 plus 0, This is negative 8 times negative 1 is positive 8. And so the double integral of f dot ds over the downward opening, the downward facing surface here is just the double integral over the region x squared plus y squared is at most 1 of 8 dA. Integrating a constant over some region just gives you the area of that region. This is a circle with area pi. Okay, so we've done the left side, we've done half of the right side. Now we need the upward facing part, the part that is the paraboloid itself. So for that part, we would parameterize it r of xy as x, y, and now we would use 4 minus x squared plus y squared. A normal vector here, we'll do rx cross ry because we want the upward pointing normal vector. Partial derivative of this respect to x would be negative 2x, so minus negative 2x would give us positive 2x, minus negative 2y would give us positive 2y and 1. F of r here, so again it will be y plus x, y minus x, 1 minus 3 times this right here, 4 minus x squared minus y squared. And so when we do a dot product of f of r with rx cross ry, this dot this will give us 2xy plus 2x squared plus 2y squared minus 2xy, and then plus 1, and then there will be a minus 12 plus 3x squared plus 3y squared. This will simplify down a little bit. That cancels out. 2x squared plus 3x squared is 5x squared. 2y squared plus 3y squared is 5y squared. 1 minus 12 is a negative 11. And when we convert this, we'll want to convert this to polar coordinates. 5r squared minus 11. So now, the double integral over the upward part here of f dot ds is going to be the double integral over, it still is the region x squared plus y squared is at most 1. We want to convert that to polar coordinates. Theta runs from 0 to 2 pi, r runs from 0 to 1 of 5r squared minus 11 r dr d theta. And when you crunch this out, the integral of the 5r squared term gives you 5/2 pi. Integral of negative 11 gives you negative 11 pi. And so putting the pieces together here, the flux of f over the boundary will be, let me write this up here, 8 pi plus 5/2 pi minus 11 pi, and sure enough, that equals negative pi over 2, which is the same thing we had there, so this checks out.